All right, let's take a look at our bell work here. So for A, looking at cosine of 22.5 degrees, how can I reformat 22.5 degrees? Probably using the half angle script that we looked at on Friday. How can I reformat this expression to be in terms of an angle that I know? Yeah, this is the same as cosine of 45 over 2 degrees. And by our half angle identities, this is going to be plus or minus the square root of 1 plus cosine of this theta, 45 degrees, all divided by 2. What is cosine of 45 degrees? That's just root 2 over 2. So 1 plus root 2 over 2, all divided by 2. This would normally fit the bill of something that I would want you to simplify. I'm okay with this kind of as is. One final piece to resolve, to deal with. What do I have left here that I need to figure out? Plus or minus the positive or negative. Where do I look for that? Yeah, we're looking at which quadrant our original angle is. So this 22.5 degrees. And which quadrant is that in? This is a quadrant 1 angle. And what do I know about cosine of quadrant 1 angles? Positive. And so this is going to be positive the square root of 1 plus root 2 over 2, all divided by 2. Some people got confused with the example that we did last time, where the quadrant of theta over 2 was in quadrant 1, and the quadrant of theta, 135, was in quadrant 2. And to that end, I would just say be very, very careful. The plus or minus and on the outside, and this plus or this minus as it is on the inside are entirely unrelated. Right? This stays positive because cosine of 45 is positive root 2 over 2. On the outside, this is positive because of 22.5 being a quadrant 1 angle. Right? So completely independent from, well, maybe not completely independent, but largely independent from one another. We are using two separate pieces of information here to determine these. Questions with A here? All right, let's attempt something similar for B. This is sine of 13 pi over 8. How can I rewrite this in terms of maybe not necessarily an angle that I know, but an angle that I can certainly work with divided by 2? Sine of what? 13 pi over 4 over 2. And so with our half angle equation here, plus or minus the square root, like that, of 1 minus cosine of, getting ahead of myself, of 13 pi over 4, all divided by 2. Is 13 pi over 4 an angle that I know? No. But what do I normally do when I end up with angles like 13 pi over 4? How can I adjust them? We could subtract 2 pi until it's an angle that we know. And so what do I get when I do 13. Now, subtracting 2 pi in this case, what's maybe a convenient way to do that? Match the denominators. I'm subtracting 8 pi over 4. And so the coterminal angle that I get here, 5 pi over 4. And what is cosine of 5 pi over 4? Negative root 2 over 2. So this minus becomes a plus root 2 over 2, all divided by 2. For the plus or minus, again, where do I have to look? We look at the original, the 13 pi over 8. Now, it might be a little bit difficult to figure out exactly which quadrant 13 pi over 8 lives in. You'd probably want to like rewrite the quadrantal angles that we have in terms of something over 8 in order to precisely figure it out. But I argue that we can pretty quickly narrow it down to 2 possible quadrants. What are kind of the 2 quadrants that we know for a fact this is going to be between? I would definitely say 3 or 4, because 13 over 8 is more than 1. So 13 pi over 8 should be more than pi. We are past quadrant 2. And in fact, we are also past 12 pi over 8, which is the same as 3 pi over 2. This is a quadrant 4 angle. And what do I know about sine in, and even if you didn't get quite to it being exactly quadrant 4, what do I know about sine of either a quadrant 3 or quadrant 4 angle? It's going to be negative. Questions with B? All right, one more. This is tangent of cosine inverse of negative 3 over 5, all divided by 2. Whenever we have an inverse trig statement, my recommendation is to break this apart into smaller component pieces. For instance, I would lead this off by rewriting this statement as tangent of theta over 2, where theta is equal to cosine inverse of negative 3/5. It's just a little bit awkward to keep this cosine inverse of negative 3/5 in our equation, so I just kind of separate it out. It gives me 2 easier problems to work with. Tangent of theta over 2. You are free to use any of the options for the half angle for tangent. The one that I default to is the one that's most cleanly sine over cosine. This is 1 minus cosine of theta over 1 plus cosine of theta. And how can I rewrite the fact that theta is equal to cosine inverse of negative 3/5? Rewrite that sentence. Reframe that sentence. No. No. I mean, like what is the? I'm just looking at how so I see what you were doing, Dylan. Sorry you're skipping a step that's going to feel very, very painfully obvious. But I want us to get used to doing this. I'm trying to rewrite what I have here. What's another way of saying that theta is equal to cosine inverse of -3/5? Cosine of theta is equal to -3/5. And what do I know about theta? Where does theta live? Second quadrant. Very good. Which will be important momentarily. All right, this is just what we do every time we run into these inverse trig functions is we're really thinking about this statement, that cosine of this angle, or that sine of this angle, or that tangent of this angle is equal to this particular ratio that we are given. Normally, we would then construct our triangle and find the mystic side, blah, blah, blah. Here, we actually don't need to, because everything that we're using is in terms of cosine of theta. We know cosine of theta is -3/5. This should be the same as plus or minus the square root of 1 minus -3/5 over 1 plus -3/5. Rewriting 1 as 5/5, this becomes 8/5 over 2/5, which we can simplify to 5's cancel, 8/2 is 4, square root of 4. This is plus or minus 2. If you want to confirm that, multiply by the reciprocal. All right. One final thing to resolve, and that is plus or minus. Okay. So what do I need to know in order to resolve the positive or negative? The quadrant of what? The original angle of theta over 2. Okay. What do I know about theta? We said theta lives in quadrant 2, which means what is the maximum value that theta could possibly be? What's the border, the upper limit of quadrant 2? 180 degrees, but in terms of radians, that is pi. Okay, so the maximum value, the upper limit of theta will be pi. And what would the lower limit of theta be? Pi over 2. So we're trapped somewhere between 180 degrees and 90 degrees, or somewhere between pi over 2 and pi. We are trying to say what's going on with theta over 2. If the maximum value for theta, the upper limit of theta, upper bound would be an even better word, is pi, then what is the corresponding upper bound for half of theta? Yeah, it's just pi over 2. It is half of whatever that upper bound is. Likewise, if the lowest that theta can get is pi over 2, then what is the lowest that half of theta can get? Pi over 4. It is just half of that lower bound. We are just dividing everything by 2. Where is this? Where's theta? Between pi over 4 and pi over 2, that's going to be quadrant 1. And what do I know about tangent in quadrant 1? It is positive. And so we are looking at positive 2. Yeah, done. It's not. It's in quadrant 2. So theta is a quadrant 2 angle. But the original angle that we are taking the tangent of is theta over 2, which if theta is a quadrant 2 angle, must be a quadrant 1 angle. Yeah, half of a quadrant 2 angle must be a quadrant 1 angle. What's the range of inverse cosine? What are the possible? Yeah, that's just range of inverse cosine. Yeah. Yeah, it's the range of inverse cosine. Other questions here? Good questions. No questions? Half angle feels okay? Especially if I'm telling you that I would give you a formula sheet for something like this on like a test that you like hypothetically had on Thursday or something ridiculous. All right. Then we are going to start our last section for Unit 5 here, 5.5. Not really anything new, although most of what we have been doing up until this point has been either like evaluating trig functions or verifying trig equations, things of that nature, verifying identities, things like that. Now we are actually going to be solving equations. Right. So looking at example 1 for the 5.5 problems that I've given you, we are looking to solve cosecant of x equals 2. Now, normally, I will give you a constraint on x. We'll talk about what on earth that means when we look at our second example here. But normally, and why we would even need that when we kind of get through our first example. So normally, x will be bound between two values. But for now, we're just going to deal with this kind of as is and, work through it without that kind of constraint. Now, we can work with this pretty directly. It does require you to be pretty comfortable with your reciprocal trig functions to the point where I think most people are probably not as kind of comfortable with those. So my recommendation would be to reformat this into sine and cosine, just because we have a more robust memory kind of catalog of unit circle and how it relates to sine and cosine rather than like cosecant or secant. So how could I rewrite this expression to be in terms of sine and cosine? Absolutely. 1 over sine of x is equal to 2. Now, 1 over sine of x, that is the reciprocal of sine of x. So if the reciprocal of sine of x equals 2, then what does sine of x have to equal? 1 over 2, 1/2. Alternatively, you could multiply both sides by sine of x and divide both sides by 2, and you would get the exact same thing. You'd get that sine of x is equal to 1/2. That is totally fine. When is sine of x going to be positive? Which quadrants? 1 and 2. And what are the thetas that we find in those quadrants that give us a y value of 1/2? In radians? Pi over 6. 5 pi over 6. Very good. Now, are these the only two possible values of x, only two angles that will give me a y value of 1/2, or have I overlooked something? And if so, what is the thing that I have overlooked? What have I not taken into account with this solution? We don't need cosine for this, though. So pi over 3 and 5, pi over 6 on our unit circle, like here and here. Is rotating by pi over 3 like this the only way that I can land at this kind of final resting point? No, okay, we could go the other direction, which would be like rotating backwards up to here. That would certainly work. What else could we do? Yeah, we could rotate around a few times and then rotate to 5 or 6. What do we call those angles that like have the same final location but have like extra rotations or rotate in the different directions? Coterminal angles. Okay, so we haven't taken into account coterminal angles in this case. Normally, how do we find coterminal angles? Add or subtract 2 pi. Is there a limit to the number of times that we are able to add or subtract 2 pi where we'll like stop finding coterminal angles after a certain number of rotations? No, we can do that as many times as we like. As long as we are adding or subtracting full rotations, full kind of intervals of 2 pi, we should have the same final kind of resting point. The way that we are going to express this in terms of an equation, we are taking what I'm going to describe as the nodes, this pi over 6, this 5 pi over 6, these two solutions, and we are going to add 2 pi times k to this 5 over 6, 5 pi over 6 and this 2 pi over 6, where the thing that we care about with k is that k is an integer. Okay, so throwback to day 1 of this class. What does it mean to be an integer? Positive or negative? So would like negative 1/2 be an integer? Whole number. Okay, so positive or negative whole numbers. Think of this as corresponding to like the number of full rotations. K tells us how many times we go around the circle. For instance, if K is 7, then I am rotating counterclockwise around the circle 7 times. If K is -15, then I am rotating clockwise around the circle 15 times before kind of finally coming to my final resting location. And so these just kind of take into account the coterminal angles. So we have like our nodes, which define like the kind of unit circle angles that we're going to care about. And then this plus 2 pi k covers all of the coterminals. And that's it. These are our solutions. Now, normally, we are not going to want every single possible coterminal angle. Normally, we'll want some of the coterminal angles, but we'll throw away the others. We're going to look at how we take that into account here on number 2. But before we do that, any questions here with our first example? Yeah. K exists, the E is like lives in. And then that bold script, it's a Z, bold script Z, is integers. It lives in the set of all integers. It just means it's an integer. Yeah. Other questions here? All right. Let's take, we'll say about 10 minutes. Take a stab at this second example here. So this is 5 sine of x equal to 3 sine of x plus the square root of 3. My advice is to start by solving for sine of x. So start by isolating sine of x, and then you're doing basically what we did with these like last 2 steps here using the unit circle. So trying to get sine of x equals something. So treat sine of x like the variable. Solve for sine of x, and then represent those. There's something that we have to do as a problem to this. Yeah, I got sine of x in terms of itself. It's like we can't have x equals in some expression. So what do we normally do before we start solving for this? Yeah, we probably want to start by writing all the numbers one side. So we just be using like this. So 2 sine. Yeah. 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 That looks good. So we could do that. This is wrong. So remember when we're like isolating something, we want all of the variable that we're trying to isolate on one side and all of the other stuff on the other side. So like you could do this, and then you could like move the non-side stuff over to the other side, and that's okay. That will work. But there's like a more efficient way to do it. Yeah, I would do that personally. But like, there's nothing wrong with what you're doing. You would just have to like slide this over by -2, and that would work. It's just more. 5 of something minus 3 of something is 1. Yeah, 5x minus 3x is 2x, so 2 times that x. All right, let's take a look at what we have here. So my first goal is to isolate sine of x. Then what do I have to do to both sides of this equation? Okay, so we need to get all of our sine of x's onto one side of our equation. I like Haddon's recommendation here of subtracting 3 sine of x from both sides. So subtracting, I get that this is 2 sine of x equal to √3. And dividing by 2, I get that sine of x is equal to √3 over 2. What are the two, we'll call them again the nodes, that I get for sine of x being equal to √3 over 2? Pi over 3 and 2 pi over 3. And what do I do to each of these to account for coterminal angles? Plus not just 2 pi, but 2 pi k to both of these nodes. Yeah, as it is right now, this is the answer. So now let's introduce the idea that I mentioned before to this problem. Not as it's written right now. As it's written right now, this is it. This is what Pearson would be kind of looking for. We'd be done. But I'm going to alter this problem ever so slightly. Let's add a constraint on x. In particular, we want x's that are between negative 2 pi and 4 pi. So now notice that not all of my coterminal angles are going to meet this added requirement. In particular, I'm not going to be able to rotate 1,000 times around my circle and expect it to fall within this kind of region that I have kind of allocated for my possible values of x. We are going to need to check to see which coterminal angles actually fall under this definition. We're going to need to test values of k to see whether or not they meet the criteria that we have set for x. So that's it. We're just going to test different values of k. Probably the easiest one to start with is let's check what's going on with when k equals 0. So when k is equal to 0, when we have not rotated at all around our unit circle, what are our two values of x that we get? Pi over 3 and 2 pi over 3. And actually, I want to do something here. I should have done this before. We're going to find as we do this, pi over 3 and 2 pi over 3 are pretty easy to compare to like negative 2 pi and 4 pi. But as we go, it's not necessarily going to be super easy to compare something like pi over 3 and 2 pi over 3 to what we have here with negative 2 pi and 4 pi. So I'm going to adjust negative 2 pi and 4 pi so that I can very, very quickly tell when I've gone beyond this kind of constraint. And the way I'm going to adjust it is I'm just going to write it so that the denominators match. In particular, I'm going to reframe this so that x is between negative 6 pi over 3 and 12 pi over 3. I'm not changing anything. This just makes it so that it's really, really clear when I have crossed beyond what I want to include. I'll know instantly. I won't have to like check. It'll be very easy. All right, so pi over 3, 2 pi over 3, are those between negative 6 pi over 3 and 12 pi over 3? Very clearly, right? 1 and 2 are between negative 6 and 12, so we're good to go. We want to include these solutions. So we'll just keep going. Let's check what's going on at k equals 1. What are my two values of x? What do I do to these two values of x here? So we're taking pi over 3, we're taking 2 pi over 3, and we are adding 2 pi. What's maybe a more convenient way to say that we are adding 2 pi? I like adding 6 pi over 3. And so I get here that these are 7 pi over 3 and 8 pi over 3. Not over 8, 8 pi over 3. Are 7 and 8 between negative 6 and 12? Yeah, so we're still happy here. We're still okay. And now we kind of can see the benefit of reformatting our boundary. It's very quick to see, are we in fact still within this? All right, let's check for k is equal to 2. When k is equal to 2, I am taking my pi over 3 and my 2 pi over 3. And rather than adding 2 pi, I am adding 4 pi. But maybe a better way to write that would be like 12 pi over 3, adding 12 pi over 3 to both. So for my first node, I get 13 pi over 3. And for my second node, I get 14 pi over 3. Do these fall within my bound? Are 13 and 14 between -6 and 12? No. And so I am done. I'm going to throw these out. And we are satisfied with the answers that we got, for the most part. Well, satisfied at the very least with the positive answers that we got. We don't need to check when k is 3. We don't need to check when k is 4. We don't need to check when k is 10, because increasing these numbers further is not going to ever put us back in between -6 and 12, right? It's not going to fix what we see. All right, so we checked the relevant positive values of k. We also, in this particular case, want to check the negative values of k. Normally, you won't need to. Normally, the constraint that I'm going to give you is between like 0 and 2 pi. So normally, checking the negatives is not a thing that we'll need to do. But in this particular case, we are going to want to, because the constraint that I gave you does include the possibility of negative angles. So we'll check negative values of k. When k is equal to -1, our nodes here, this pi over 3, now minus 6 pi over 3, and 2 pi over 3 minus 6 pi over 3, I get that these are -5 pi over 3 and -4 pi over 3. -5 and -4, is that between -6 and 12? Absolutely, yes, it is. So we would want to keep these two solutions as well. We're pretty close to the boundary, so probably subtracting another one is going to take us over, but we'll check it here. When k is -2, we are doing x is equal to pi over 3 minus 12 pi over 3 and 2 pi over 3 minus 12 pi over 3. I get -10 pi over 3, not in this order, -11 pi over 3, and -10 pi over 3. Are -10 between -6 and 12? -10, -11? No, they are not. So we do not want to include these. These are outside those constraints. And so the only negative value of k that we need to worry about in this case is -1. And so what do we have? Well, we have 6 different solutions for x. We have 2 solutions when k is equal to 0. That was pi over 3 and 2 pi over 3. We have 2 different solutions when k is 1. That was 7 pi over 3 and 8 pi over 3. And then we have 2 solutions when k is -1. That's -5 pi over 3 and -4 pi over 3. So 3 sets of coterminal angles here. And these are the ones that we'd have to worry about. Is that a question, Simon? Yeah. So could you write like pi over 3 plus 2 pi k, where k is like -1, 0, and 1? I'd accept that. Yeah, I would accept that. And I promised fourth period that we'll look at an example tomorrow where I show you how to find the constraints on k given the constraints on x. We'll look at an example like that. It's kind of cool. But this kind of way of just going through and checking the different values of k is what I've recommended most people to do. But I'll show you the other way as well. Other questions here with our constraints, with checking the values of K. So. All right. The Pearson problems that you guys are going to do don't really give you constraints. I will generally give you actually like one set of constraints. So negative 2 pi to 4 pi is a weird one. That's generally not what I'm going to give. What you'll see from me is a lot more like what you will see in example 3, where we are looking at sine of 4x equal to 1/2, given the constraint that x is between 0 and 2 pi. Yeah. So we're gonna see that this is a relevant constraint. So if this were like just sine of x equals 1/2, this would basically be telling us that we don't want to look at coterminal angles. We just want to look at what's going on the unit circle. That's still kind of what this is saying, but we're going to see that these are very much not unit circle angles that we end up with for x. And we'll see kind of in a second here how we have to adjust this constraint. So big difference here. What is the difference other than the presence of this kind of we live between 0 and 2 pi? What's the big difference between this and what we did in problem 1? Yeah, the 4x is going to be kind of the weirdness that we are adding here, that we are introducing. And honestly, it's not super easy to deal with directly. And so I'm going to do what I kind of have consistently recommended whenever we have a problem that has a fair bit of kind of complexity built into it. And that is, I am going to set aside the complexity temporarily. This is very, very similar to kind of what we did here, where I set aside this complicated cosine inverse of -3/5 and dealt with that separately. We're going to do something similar. We're going to use what's called a dummy variable to temporarily take the place of 4x. We're going to solve this equation in terms of that dummy variable, and then at the end we'll actually solve for x. This isn't the only way to do it, but this is kind of how I would recommend doing it. Because of calculus, the dummy variable that I am going to choose is u. So everywhere I see a 4x, I'm going to replace it with u. We're basically setting aside the 4x here. So I'm going to rewrite this as sine of u is equal to 1/2, where u is just 4x. We're just taking that 4x, we're setting it aside. We'll deal with them later. Now, x is between 0 and 2 pi, but we're not solving this in terms of x anymore. We're solving this in terms of our dummy variable. So we need to redefine the constraints on our variable that we have here. If the lower bound for x is 0, then what is the lower bound for 4 times x going to be? It's also going to be 0, yeah. So u, the lowest u can become, is 0. And if the upper bound for x is 2 pi, what is the upper bound for 4 times x going to be? 8 pi. Very good. This is just times 4. Very good. Whew. All right. So sine of u is equal to 1/2. What are the nodes that we get here for u? Pi over 6 and 5 pi over 6. Very good. But what do I have to remember? Well, u is going to be between 0 and 8 pi, which we'll adjust for. What do I add here to check for coterminal angles? 2 pi k, we'll add 12 pi over 6 until we're not able to anymore, basically, yeah. We're going to add 2 pi k. We're going to check the various values of k. Like Haddon suggested, 2 pi might be more conveniently written as 12 pi over 6, which I like a lot. And 8 pi can be more conveniently written as what? What's going to tell us that we've gone over? Very good. 48 pi over 6 is going to be that upper limit that we'll use to check when we have gone too far. Okay. So now we just have to check our values of k. Do we need to worry about negative values of k here? If the lowest that we can get is 0, then our angle can never be negative. We're never going to be subtracting 2 pi and getting an answer that we worry about. Negative values of k are not going to yield us solutions here. So let's just start at when k equals 0. What are the two values of x that I get when, or not x, sorry, of u that I get when k equals 0? Yeah, that's just our kind of almost reference angles here. When k is equal to 1, we are adding, we said 12 pi over 6 to both of them. Pi over 6 plus 12 pi over 6 is 13 pi over 6. And 5 pi over 6 plus 12 pi over 6 is 17 pi over 6. Am I close to 48 pi over 6 yet? Not really, so we can keep going. When k is equal to 2, we could think of adding like 24 pi over 6 to the originals, but we could also just think of adding like another 12 pi over 6 to what we just found. Adding another 12 pi over 6, u is going to be 25 pi over 6 and 29 pi over 6. Exact same thing for when k is 3. So adding another 12 pi over 6 here. This is 37 pi over 6 and 41 pi over 6. We're getting kind of close, but have we hit 48 pi over 6 yet? Nope, so we can keep going. When k is 4, adding another 12 pi over 6, I get that u is equal to 49 pi over 6 and 53 pi over 6. And what do I notice? We've gone over that parameter that we set, that 48 pi over 6. We would not include these two values. Okay, so I have 8 different solutions for you, 2 of which from when k is 0, 2 from when k is 1, 2 from when k is 2, 2 from 1k is 3. Now, what's wrong? Am I done? Like, essentially, am I done here? Have I solved the problem? Are we finished? Yeah, we're still in terms of our dummy variable, right? We haven't found the values of x that solve our equation. We found the values of this other variable u that we are using in place of x temporarily. We have to readjust now for x. So everywhere we have a u, well, really, these are all just going to be equal to 4x. And so what do I have to do to each of these values in order to solve for x? Divide everything by 4. Dividing by 4 is the same as multiplying the denominator by 4. And so my 8 solutions for x are going to be pi over 24, 5 pi over 24, 13 pi over 24, 17 pi over 24, 25 pi over 24, 29 pi over 24, 37 pi over 24, and 41 pi over 24. Which are all between 0 and 2 pi. You can confirm that. Now, this is not the only way that we could have done this. In fact, we're going to look at kind of the other way and what Pearson would have you do, given that they are not going to ask you for this with a constraint. So the other way does not require us to use a dummy variable. The other way just jumps straight into this idea that, well, we know that 4x is going to be equal to pi over 6 plus 2 pi k, and that 4x is going to be equal to 5 pi over 6 plus 2 pi k. We did the same thing, but we used u, and then we readjusted for u and blah, 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 blah. And what we can do here is just solve directly for x. And in fact, without a parameter, this is basically what you would need to do. Dividing both sides by 4, I get that x is equal to pi over 24 plus 2 pi k divided by 4 is going to be pi over 2 times k. And I get 5 pi over 24 plus, again, this factor pi over 2 times k. And then we could check, we could add pi over 2 until we are outside of being between 0 and 2 pi, and we would get the exact same set of solutions that we see. And so that would also work. That's kind of the way to do it without doing u substitution. And this, without our parameter, would be kind of the representation for all of the possible values of x that we could end up with. But on like a test or quiz, or I guess tests that we have on Thursday, I will give you a parameter. And so the way that I kind of recommend is to set aside the complicated inside bit, deal with that later. First, deal with the whole business of in terms of the dummy variable. Yeah, super. You could substitute in, so like and we'll look at how we could do it directly with K. You might notice a pattern, you could look at like the number of rotations that we have between 0 and 8 pi. 4 full rotations. So every full rotation gives us 2 answers. You'd expect to get 8 answers. So that's kind of like one way that you could look at it. We'll look at how we can solve for the constraints on K. We'll do an example where we look at that tomorrow. But certainly there are ways that we don't have to be quite as brute forced with it as I am currently being. Good question. Other questions here? All right. So we've got about 10 minutes left. You guys have the 5.3 through 5.5 Pearson currently uploaded. That is due on Wednesday. So we'll finish up 5.5 tomorrow. So working through the Pearson, and then we'll have a study guide uploaded some point tomorrow, and review day on Wednesday. All that.